All right. Hello, everybody. Welcome to this ISRM Young Members monthly seminar series. And we're just after the hour, so let's get started. So welcome to the fifth session of the ISRM Young Members seminar series. My name is Jennifer Day. Federico Vagnon from Polytechnic of Turin, Italy, and I from Queen's University in Canada, as part of the ISRM Young Members Group, are happy to chair this fifth monthly seminar. It is a great pleasure for us to be here today, and we would like to thank you for attending this fifth session. Before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Dakoda, the ISRM Vice President for Australasia and Chair of the ISRM Young Members Committee. We would also like to thank all young member representatives of the national groups that have joined this initiative from Spain, Australia, New Zealand, Japan, China, Chile, and Canada, among others. Finally, we would like to thank Dr. Massud Raju and Mr. Juan Jose Manal for agreeing to present their work in this session. Before our speakers begin, I'll take a moment to present key information about the seminar series. This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for the speakers is as follows. The speakers must be an ISRM member, have a maximum age of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics or rock engineering for a period no longer than 10 years. Speaker nominations can be made by the nominee's national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see our contact email. This webinar will be held every month, and we invite you all to keep in touch. We will now begin the first seminar of the day. Each presentation will last about 20 minutes and will be followed by 10 minutes of questions and answers. For the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any questions, please use the chat and the raise hand feature. Okay, let's move on. Our first speaker is Dr. Massud Raju, who is a rock engineer with special interest in the mechanics of rock failure and numerical modeling. He is currently a rock mechanics specialist at AECOM Canada and contributes to the tunneling projects in North America and beyond. He has a BSc in mining engineering and MSc in mining rock mechanics. He received his PhD in rock engineering from the University of British Columbia, where he developed a new theoretical framework for understanding and modeling the 3D directionality of brittle rock fracturing and mobilization of rock strength and dilation. During his MITAX postdoctoral fellowship at UBC, he developed a new tool for evaluation of brittle fracturing for the Grasberg DMLZ block cave mine. Since then, he has been developing a new method for estimation of rock mass peak and residual strengths with application to jointed and veined rock masses. Today, he will be presenting a talk entitled Directional and 3D Confinement Dependent Fracturing, Strength, and Dilation Mobilization in Brittle Rocks. Dr. Raju, the floor is yours.
Hello and good morning, good afternoon, good evening, everyone around the globe. Thank you, Dr. Day, for introducing me and ISRM Young Members Committee to inviting me for this presentation. Today, I'm going to talk about the research that I conducted during my PhD around the topic of the 3D confinement-dependent fracturing, strength and dilation mobilization in brittle rocks. First, I will talk about the motivations of my research, and then I move on to some of the obstacles as I see them for the rock engineers around the globe, which are the paradigms in rock engineering that are preventing us to go forward. And it held me back as well for a while. And then I will explain the conceptual models and ideas that the framework that I developed to understand how the 3D confinement affects 3D fracturing, and consequently how the strength of brittle rocks is affected by this type of fracturing, and as a consequence, again, the directionality of dilation characteristics.
Excuse me, Masoud, sorry to interrupt. I can't see your slides. Would you mind
I'm so
checking if they're
sorry.
sharing, please?
Okay, I'm so sorry that it didn't come in. Can you see my screen now?
Perfect. Thank you very much.
Awesome.
We see your outline slide.
Thank you. Awesome. Sorry for that. So about the motivation. So about we are designing rock in different rock masses, whether they are weak or jointed or massive. We've developed different design and construction approaches specific to each, and we have successfully done that in the past century, essential. In the past decades, we've focused on deep excavations. The diagram shows here is the cave mine's undercut depth that the depth has increased in the past years, in the past 2 decades, and they're reaching the depths that we've never worked in. So first of all, the stresses at this environment is very high, are very high, and the rock mass is less jointed. And we don't have that much experience in these depths until we, adjust our design and construction methods. In specific, my interest was in hard rocks, which are susceptible to spalling and bursting, and excessive deformation as a result of that. So I focused specifically on hard rocks and how they fail. The dual nature of fracturing in brittle rocks is interesting. We know that rock fails under confinement in shear modes. That's one side of the idea, and under tension it fractures with extensional fracturing. However, there have been observations in the past 50 years about the formation of extensional fracturing just at the shell or the perimeter of the excavations under confinement. And these are the main interest of many engineers, because the formation of these fractured rocks affect the support system, and basically it can be a hazard as well if the fracturing progresses in a violent manner. So to understand the mechanism better, I looked at the data that was available at the time. Here is the data for the West Lily granite polyaxial test data. Data results are shown on different coordinate systems, principal stresses, differential stresses, as well as the divergent or octahedral plane, and in a normalized fashion as well. In these polyaxial tests were conducted between 0 and 100 megapascal of sigma 3, and sigma 2 was increased to a level that was achievable by the machine at the time. The markers enlarge with the confinement level. So for 0, we have low confinement, very small markers, goes up, gets larger, and the color here shows the angle of fracture plane after failure. As you see, interestingly, with increase of confinement, sigma 3, the colors become pale, meaning that the fracturing becomes, fracture angle becomes lower. With increase of sigma 2, however, the colors become more purplish bluish colors, specifically in low confinements, as you see, and meaning that the fracture plane gets steeper, basically sometimes 90 degrees. Now, if we look at the Coulomb's hypothesis, this fracture plane, um, we expect, according to this hypothesis, that form with an angle of 45 plus 5/2, and if we go for a maximum friction angle of 50, the maximum fracture plane angle would be 70 degrees. Now, as a rule of thumb, 70, 75, if we get that as a maximum angle that is justifiable by Coulomb's hypothesis, we can basically find the transition point from extensional fracturing to shearing or shear fracturing, as shown here with the dotted line here. Now, if we look at the octahedral plane, we see that the zone that is this shear fracturing hypothesis of Coulomb's is applicable is very narrow, very close to the triaxial compression line or meridian. And then as soon as sigma 2 increases, we are ending up in extensional fracturing. So which is not justifiable or interpretable with the Coulomb's hypothesis. Interestingly, the influence of sigma 2 has been studied and explained, and many criteria were developed. However, the deformation and dilatancy, or the rate of uh, opening and dilation was not measured during the test because of the lack of equipment until recently. So when we look at the influence of 3D confinement on the fracturing modes, that we can summarize it in this figure. The blue line is the triaxial compression, which is a symmetric stress state where sigma 2 is equal to sigma 3, and the other one is the triaxial, the magenta is the triaxial extension, which is again symmetric, sigma 2 is equal to sigma 1. And the other stress states sit in between. With the increase of sigma 3, we get from extensional fracturing to shear fracturing. And with the increase of sigma 2 under confinement, we go from extensional fracturing that we had under low confinement, and which becomes like planar slabbing kind of shape of fracturing. Under higher confinements, we go from shear fracturing to extensional fracturing as is shown here. And please notice the amount of confinement that extensional fracturing is expected to happen. Now, there are a few paradigms in rock engineering, as I mentioned, about the fracturing mode, about the dilation or compaction, about friction and cohesion, fracturing under biaxial stress conditions, and how it can be interpreted to a 3D stress state, failure of the rock mass under 3D stress state, and how we model it. Today, I'm just going to talk about the first two, the fracturing mode and the dilation and compaction with regards to the topic of my research. So the paradigm with regards to fracturing mode is that the extensional fracturing occurs under tension and shear fracturing occurs under confinement. However, extensional fracturing under low confinement that has been observed cannot be justified or interpreted based on this kind of paradigm. And again, we have along this dotted line in this more diagram that shear criterion is assumed to be applicable without any evidence of applicability. This paradigm, as I showed for the failure modes that I summarized, has a jump, as I mentioned, that ignores the extensional fracture under low confinement. And if we assume that the symmetric fracturing is captured by Coulomb criterion under TC and TE, Then there is a jump between triaxial compression stress state to asymmetric stress state, and from that to triaxial extension or extension um, symmetric stress state in terms of failure mode. These shifts and stepwise shifts assumed for fracturing basically govern the way that we formulate the yielding model and the constant model, basically yielding model and dilation model in the codes. Now, with regards to the fracturing, what I did, I looked at the Coulomb's criterion in a different way. So I looked at rewrote the Coulomb's criterion based in terms of the effective shear stress, and then modified it to capture the multidirectionality of that. So here is the Coulomb criterion. The interpretation here is that we get the maximum circle, Mohr circle, and then here is the friction law, linear friction law. The maximum, we are looking for the maximum effective shear stress, which is found by finding the tangent to this circle parallel to this line. The meaning of this criterion in 3D stress state is the envelope of the Mohr-Coulomb criterion as shown here. As you see, it's a kind of a conical shape, and it is sigma 2 independent as expected. And the meridians under triaxial compression, triaxial extension are shown here. Now, to modify it, I assume that, okay, instead of only using the maximum effective shear stress on the largest circle, I use whatever effective shear stress on the circles wherever they are positive. So basically these 3 points. And again, the criterion as shown here. The envelope of this criterion is smooth as shown here. And again, it's conical, but the transition in terms of strength is very smooth. And most importantly, sigma 2 dependency of the strength is captured in this criterion. So what was missing from Coulomb's criterion was the fact that it is not only one direction favorable for fracturing, but there are other orientations favorable as well, maybe not as much, but they are still favorable and fractures can propagate. And it is a summation and overall effect of fracturing along all these favorable orientations that gives you the strength of the overall strength of the rock. To make it a little bit more fancy, I looked at the possibility of making the friction law nonlinear, and as a result, as you see, the friction law is a function of sigma n, basically. And as you see, the confinement dependency of the criterion is achieved. Again, it's sigma 2 dependent, is capturing the octahedral behavior as well. With regards to the fracture mode under extensional fracturing, I looked at a parameter that can be negative under confinement as well. So I looked at Maria's maximum axial extensional strain, but it was not enough because it is for the tensile stresses. And then I looked at Navier's maximum lateral extensional strain, which means that under axial confinement or under axial compression, the lateral extension can be used for the criterion. I modified this criterion to capture the confinement dependency of the criterion as well, with application of confinement in the direction of extensional strain. Basically, the rock gets more strength, and fracture requires more extensional strain to cause fracturing. The envelope of this criterion, as an example given here, is concave, surprisingly, and but in the low confinement, as you see, it is a triangular shape in the octahedral plane, and the sigma 2 dependency is captured. Then I combine these two, and by combining these two, we get a 3D criterion that is applicable to extensional fracturing as well as shear fracturing. Please note that the S-shape curve characteristics of this curve in low confinement, it is mostly the extensional criterion applicable for extensional fracturing, and then it switches and transits to shear fracturing, which is again 3D. I modified the existing criteria to capture these S-shaped characteristics as well. I used 3D Hook Brown and Moore Coulomb, 3D Moore Coulomb. Here I show the 3D Hook Brown criterion. As you see, it is altered in a way that it captures that S-shaped characteristics. The other paradigm that I had to deal with regards to understanding the behavior of the brittle rocks is related to the definition of dilation and compaction. Dilation and compaction are basically a means of understanding how the relative straining of the material. For example, for a given shear straining, how much volumetric change is happening, or for a given increment of axial compaction, how much lateral dilation occurs. Reynolds hypothesized this concept back in 1885, but for the past 140 years almost, the dominant approach to dilation has been volumetric. So when you, even the term dilation in the minds of all geotechnical engineers or other engineers who are working with deformable material, basically solids, they take it as volumetric. However, the directionality and directional definition of that is also important as very meaningful. The volumetric definition has been used for soil, concrete, and porous material. However, for non-porous material or low porous material like rocks, the directional component of that is important for us. In the context of plasticity theory, the ratios are defined based on the plastic strength increments. And the simple understanding of that is like Poisson effect. The directional definition is like Poisson effect. For a given increment of compaction in axial direction, how much, what's the increment of lateral extension? And it's very important for us rock engineers when we think of practical cases. For example, here is a tunnel, and we want to see how much radial deformation we get. And the ratio here provides us with a means to understand, okay, for a given amount of tangential compaction, how much radial convergence we get. Most importantly, we are interested to know how much confinement can prevent this amount of dilation, and if it is enough. So basically, that is kind of thing, a very important concept for design of support system. As I said, under uniaxial compression, the terminology and the definition can be is illustrated here. The ratio nu to 1 plastic is the increment in the direction of sigma 2 versus the increment in the direction of sigma 1. And because the lateral direction is extending, the negative sign is added so that the ratio is positive when they're acting in different ways. Under uniaxial compression states or all triaxial compression symmetric stress states, nu2 1 and nu3 1 are identical. There's another case of triaxial extension, which is again symmetric, but in this case, sigma 2 is equal to sigma 1, meaning that in sigma 2 and sigma 1, we have compaction, and we only have dilation in the direction of sigma 3. The amount of dilation that we get in the direction of sigma 3 is much larger compared to the case that we have triaxial compression case. With increase of sigma 2, there is one intermediate kind of stress state at which the influence of sigma 2 is that it diminishes the amount of dilation that we got under triaxial compression. And basically, the amount of all dilation goes towards the direction of sigma 3. With increase of sigma 2, we see that a decrease in nu2 1 and increase of nu3 1. We can take this case to a 3D confinement case. In general understanding of that, the red rectangle is the case that we just talked about, with increase of sigma 2, increase of nu3 1, and decrease of nu2 1. Now we are interested to know how confinement affects dilation. With increase of sigma 3, basically, we expect that it is held, the material is held, whether under fracturing or not, and then we get a lower amount of nu3 1 and nu2 1. The phenomena is illustrated with these cubes. Again, the case that we have plastic strain, plane strain condition with d epsilon 2 equal to 0 is shown here. The uniform dilation model is one of the most used models in constructive modeling nowadays. In this uniform model, the dilation angle psi is used as a constant value. The thing is, because it is constant, it ignores the influence of sigma 3 on dilatancy. However, it captures the influence of sigma 2 in a stepwise manner. Here is the relation between nu3 1 and nu2 1 for different sigma 2 values. The influence of sigma 2 is captured here with the stress ratio B. When sigma 2 is equal to sigma 3, triaxial compression, B is 0. And when sigma 2 is equal to sigma 1, we are dealing with triaxial extension, and B is equal to 1. This formulation shows that for a case, for example, of a dilation angle of 36.87 degrees, dilation angle under triaxial compression is nu3 1 is 2, and it jumps to 4 as soon as we get to asymmetric stress conditions, whether sigma 2 is not identical to sigma 3 or sigma 1. And under triaxial extension, again, it jumps twice, it becomes 8. Under triaxial, under triaxial compression, nu2 1 is equal to nu3 1, and then as soon as it gets asymmetric, it drops to 0, because essentially the model is sigma 2 independent. And this sigma 2 independency of this uniform model is captured here, as well as here, but it's 0, the epsilon 2 becomes 0, basically. And then under triaxial extension, it becomes -1. The trend is that nu3 1 is increasing with sigma 2, increase of sigma 2 or B ratio, and nu2 1 decreases from whatever value they have to under triaxial compression to the value that they have under triaxial extension. The important point here is that there is a stress state at which the epsilon 2 plastic becomes 0, and basically it differentiates the behavior of sigma 2. For stress states where B is less than, for example, in this case, 0.2, sigma 2 acts like sigma 3. Basically, we have dilating in both directions. And as soon as it transfers or transits to the cases where B is higher than 0.2, in this case, sigma 2 acts like sigma 1. It's acting like sigma 1. And its influence on fracturing, basically, and dilation is identical to the influence of sigma 1. Here I show the calculation that I did for nu3 1 and nu2 1 using a potential function. The potential function I use here is the late criterion, and I calculated the gradient and then calculated nu3 1 and nu2 1 using the values that I had. The trends that I explained before are visible here. With increase of sigma 3, we see a decrease in nu3 1 and nu2 1. And with increase of sigma 2, we see that the color goes from darker to pale. more pale ones, and you see that it goes to higher values on nu31, and basically it comes from whatever value it had to -1 for nu21. There is a specific angle here, or stress state, theta star, which is related to that B, that gives the plastic plane strain condition, which this angle for this example that I solve is 22 degrees, meaning that for the theta values or stress states close to TC, sigma 2 is acting like sigma 3, and after that, sigma 2 is acting like sigma 1. And that is what this illustration captured. So to conclude, I can say that the 3D confinement affects the 3D fracturing mode. And these fracturing modes basically shape the way that we think about the strength of the rock mass. The ignored cases of failure under low confinement, which are extensional modes, can be captured using an extensional strain criterion. The extensional strain criterion presented is 3D, meaning that it is 3D confinement dependent. And the shear fracturing is also 3D by capturing and understanding that the shear fracturing is a 3D mechanism and is happening all febrile orientations. By combining these two, we can get the full spectrum that we wanted to have. Again, 3D confinement caused 3D fracturing of the rock with different modes, and these modes are basically comparable to the dilation framework that I present. Under lower confinement, where we have extensional fracturing, we have whatever value we have for nu31 gets higher. This nu31 gets higher as soon as the extensional fracturing goes to become more like slabbing. And with increase of sigma 3, we go under triaxial compression, we go from extensional fracturing to shearing, and this is captured by decrease of nu31 as shown here. And then under triaxial extension, again, we are going lower nu31 values, and to go from higher nu31 values that we had, for example, here is 8, it goes to 5. But again, with increase of sigma 2, we are going to transfer from extensional shear fracturing to extensional fracturing, and this is corresponding to the transition of nu31 from lower values to higher values. Practical significance of this framework is that whenever we are dealing with fracturing of the rock and massive rock masses, and we like to know what's the depth and deformation of the excavation damage zone, we need to understand that fracturing is a 3D phenomenon. Because of the febrile orientations, permeability and solute transport, it has preferred orientation with regards to the fractured form in the rock mass. Directional dilation gives, and this framework gives an understanding how we can understand the deformation of the fracturing rock around the excavations under different stress states. And we can come up with solutions for support design so that by increase of confinement, we can withhold the rock mass in its place. Finally, we can put these understanding together and develop a constitutive model that represents the fracturing and behavior of the massive brittle rock masses, hopefully in the near future, so that we can present safer mines and more profitable mines for all. Thank you so much for your attention. I would like to thank Professor Eberhard, my supervisor at the University of British Columbia, and my supervisor committee, late Professor Hunger, Professor Elmo, and Professor McDougall. I would like to thank Dr. Kaiser, Professor Dietrichs, Dr. Chandler, Dr. Wu, and Professor Walton for very, very constructive discussions that we had, and the friendship and encouragements I received from all my colleagues. Links to my dissertation is provided here. Thank you.
Thank you very much, Masoud, for an excellent talk. We now have 10 minutes for a question and answer session. Does anybody on the call please have any questions? While some of you may be trying to think of some questions, I have one for you. This is excellent work and certainly an advancement of constitutive models and rock mechanics. I'm curious as to how you envision this work being incorporated more into rock engineering practice.
Awesome question. You're pointing out basically to the 3 paradigms that I left out, which are with regards to how we model yielding of brittle rocks. The existing paradigm is that cohesion and friction mobilize at the same time, and the way that most people are doing this work is that they're doing this co-mobilization of a synchronized mobilization of cohesion and friction. However, the work of Haji Abdul Majid, Martin, Didrix, all these great researchers show that we have to move on to cohesion, weakening, friction, strengthening concepts and use that. The other thing is that there is an era in rock engineering that we had to rely on theories. We didn't have the luxury of having true triaxial machines. And we had to rely on theories. So at that era, around 40 years, we tried to bring whatever theory that we had in fracture mechanics and apply that to rock engineering. And sometimes those theories are not exactly matching the reality of the behavior. The case of biaxial stress condition is one of that. There are many cases that you see the criteria were developed for biaxial stress condition, which means that you have a thin plate of rock or material. And then because of lack of material, basically fractures do not form in a way that we expect in a 3D body where we have enough material to form. So those criteria, like Griffith criterion, that has been extended to be used for general case, we should look back on those theories and revise their applicability. The other thing is that with numerical modeling, advances is that we see in numerical modeling. In the past decade, we have moved from continuum modeling drastically to discontinuum and hybrid modeling. And now is the time that we don't stop ourselves in 2D modeling, because again, the assumption here is that fracturing cannot propagate out of the plane, which is clearly not the case in general condition where you have the rock mass, and when you're under the stress path that it experiences, fractures can form in any direction. Now, the implications of these 2D modeling is, in my belief, are preventing us from moving forward. The way that they are calibrated using triaxial compression tests is not, in my belief, the correct way of calibrating these codes, because when you consider the case that I showed, one of the examples that I can probably share with my friends here is that the case of this plastic plane strain case, where you don't have any out of plane strain, is the case that we are modeling in 2D when you have fracturing. Under this case, the strength of rock mass is higher than the case of triaxial compression. And the amount of dilation that this gets is at least double the value of dilatancy that you get under triaxial condition. So when you calibrate your model using triaxial compression tests, while the reality of behavior is this one, gives you wrong results. If you get the same parameters and run a 3D model, you will get different values, which seem to be controversial, wrong, or in your mind, but the reality is the code capability prevents us to go forward. So I suggest, and what I see in the future, and I hope that we move fast, is that we get out of this 2D modeling and present the real behavior using 3D modeling.
Very good. Thank you, Masoud. I hope to see that day come soon.
It will, I'm sure.
Perfect. Does anybody have any other questions for our speaker?
I have a curiosity, if I can.
Please.
Yes.
Okay, thank you very much for your presentation, also for the clarity in your speech. My question is, did you perform any test to validate this new criterion? And if yes, which kind of rock did you use?
Yes, with regards to triaxial compression strength criterion. If I may, please, I bring the dissertation here. So there are data in the literature for polyaxial test data that we can use to verify the applicability of the criterion and find the parameters and fine tune it. In terms of the transition between the transition from extensional fracturing to shear fracturing, there are limited way of finding it. People find this transition in different ways. Dr. Chandler and his team at URL did a long-term controlled damage test to find. Oh, sorry. Do you see my screen? I'm just curious. Do you see my screen in my PDF?
We see the PowerPoint.
PowerPoint. I'm sorry.
We see the dilation, compaction, 3D directionality.
Yes. I'm sorry. 1 second. I'm going to share the other slide. Screen 1, maybe. No. Screen 2. Yes. So now you see that, right? You see my PDF,
yes.
Right? Okay. So
yep.
Dr. Chandler tested, under basically controlled tests, basically this is a creep test kind of a way that he increased the level of sigma 1 and waited until it fails, and found the failure. Developed the envelope for these tests. Short-term tests versus long-term tests show that the decaying strength is not that much under higher confinement where shear fracturing is expected to happen, versus in low confinement, there is clear reduction of strength, right? So that idea about S-shaped curve is kind of captured in his results. What I did, I used triaxial test data that, again, Professor Chandler performed, and plotted the results in a way that are shown here. Is shown here. So sigma 1 versus sigma 3, crack damage, initiation, crack damage, or volumetric reversal, basically. And this is peak. Now, by plotting sigma 1 of each of these curves versus sigma 1 peak, you can find the stress confinement, basically, at which a transition between spalling to shearing happens. So basically, when you plot the crack initiation, you see that it decays and gets a constant value, whereas the other one is for the crack damage or volumetric reversal is constant. The other way to plot it is plotting sigma 1 over the crack damage. In this case, you see that this way, you see that the other plots go up and gets to a constant value. Or sigma 1 versus sigma volumetric reversal. Now this is 1. And then again, you see that there's a spalling to shearing. So there is a way to find that spalling to shearing limit. Numerically, people have done that as well. Professor Diedrichs did that, as well as many others after him. Still, there is not a standard method to find this method. I've not seen that yet. Maybe in the past year, I was involved in consulting. Something came out, but I have not seen that. With regards to dilation, it is more tricky because under the measurements of lateral deformation is much easier when you have triaxial compression condition. But when you can install, the transducers or chain, use that, measure that. However, when it becomes true triaxial with platens, measurement of that was hard until like 5-7 years ago, that people started to measuring that. So basically what I'm offering is a hypothesis here that and a framework for more work. At the end of my research, I saw a publication from the team of Professor Feng from China that he did some analysis on the plastic strain increments ratio in true triaxial tests. But still, this is something that is going forward. With regards to constitutive modeling, this framework gives us some boundaries to know which criterion to use, which one would not work. For example, if you use Drucker-Prager criterion, you might get very, very large sigma 2 dependency kind of behavior, as shown here. And this framework can limit us, not going this much high on the strength curve. On the strength side. On the dilation side, again, the framework that I presented gives a correct understanding what are the boundaries to be used, again, for Drucker-Prager and as used as potential function or other models and formulations. It gives us clear understanding what is happening and how to parameterize the constitutive model that is not wrong if it's not right. I hope I could answer your question.
That's great. Thanks very much, Masoud. Thanks everyone for your interesting questions, and thanks Masoud for your very engaging answers. I unfortunately must say we need to move on to our next speaker, and I will I'll share my screen and let Federico introduce what's coming next.
Thank you very much.
Thank you, Jennifer. Thank you, Masoud. Let me share my screen. Okay. Thank you, everyone, for your question. Let me introduce the next speaker of this webinar session. The next speaker is Mr. Juan Jose Monsalve. Unfortunately, today he cannot attend the seminar and present live his work due to work commitments. However, he sent us a video recording of his speech, so we can still appreciate his research. Juan is a Colombian mining and metallurgical engineer from the National University of Colombia, with a master's degree in mining engineering from Virginia Tech. Juan has worked as an engineer assistant in geotechnical design company in Colombia, gaining experience in rock mass characterization and numerical modeling for underground excavation. He is currently pursuing a PhD degree at the Virginia Tech. His current research is focused on the integration of laser scanning with stochastic discrete element numerical modeling to evaluate and assess rockfall hazards in underground tunnels and pillar failure in underground mines. Juan has served as the president of the ARMA student chapter at Virginia Tech. Today, he will be presenting a talk entitled Stochastic Discrete Element Modeling for Pillar Strength Determination, a first step in a risk-based pillar design approach. So I share with you the video.
Good morning. Thank you so much for today's invitation to this 5th ISRM Young Member Seminar. In today's presentation, I will present some of the work I have developed during my PhD. This presentation today is entitled Stochastic Discrete Element Modeling for Pillar Strength Determination as a first step in a risk-based pillar design approach. I would like to say that this research is part of a parent project that was funded by the National Institute for Occupational Safety and Health as a part of a ground control capacity building project, which its main objective was to develop capacities to improve design strategies for underground stone mines in order to improve safety. I would like to acknowledge all our industry partners and academic partners, including NIOSH, the Virginia Tech Mining and Minerals Engineering Department, LUOS North America, Itasca Consulting Group, and MapTech. The following is the content for today's presentation. Pillar design is one of the greatest challenges during the planning and development of an underground mine project. Not only the dimensions of the pillars should ensure the stability of the mine, but also should maximize the reserves. A pillar failure is a low probability of occurrence event in comparison to other ground control instability issues such as rock falls or ground collapses. Nevertheless, their consequences are far more severe. The collapse of a pillar often leads to the collapse of its neighboring pillars, also known as a cascade pillar failure. Not only pillar failures have killed and caused serious injuries to workers, but also they have generated surface subsidence and sterilized valuable reserves. Common pillar design trends are based on empirical approaches, and these relations are designed in most of the cases based on site-specific conditions and are only applicable under certain specific circumstances. These equations are unable to represent different failure mechanisms that can occur in pillars and do not consider geological and geotechnical uncertainty in the rock mass. As a reflect of this, pillar failures continue to occur, both within the US and internationally. In the past 5 years, there has been 5 massive pillar collapses in the US. This has raised the awareness and the attention of the Mine Safety and Health Administration, MSHA. They developed an initiative called the Pillar Collapse Initiative, a dedicated website focusing on raising awareness on these issues and share technical content to prevent these events to continue to occur. As we can see, pillar collapses are events that can be referred to as high-risk events. Due to that pillar collapses are high-risk events, their design and maintenance should be addressed from a risk-based perspective. This work proposed a risk-based pillar design approach based in laser scanning and virtual discontinuity mapping, stochastic discrete element modeling, and stochastic finite volume modeling to estimate pillar stress variability. Today, I will be presenting some of the results obtained from applying this methodology in a case study mine. In this section, I will briefly introduce the case study mine, design, and geomechanical parameters that were used as inputs in different analyses of this project. The case study mine consists of a room and pillar with eventual stoping. In the areas of the mine where the limestone seam is consistent and thick enough, 12.8 meters wide and 30 meters high stopes are conformed. The open stopes are supported by squared 24 meter wide and 30 meter tall pillars. The main ground instability hazard encountered in this case study mine are related to the presence of discontinuities and karst features. Due to the presence of clear discontinuity network in the rock mass, the main failure mechanism defined was structurally controlled. The table below summarizes intact rock mechanical properties for the three main lithologies. This data was provided by the mining operator and consisted of 6 density test results, 6 uniaxial compressive strength tests, and 6 Brazilian tensile test results for each lithology. This information was used as inputs for the different analyses and calculations. The data was limited to the number of samples mentioned, and it was not clear where the samples have been collected from. Due to the structurally controlled failure mechanism, a laser scanning campaign took place in the case study mine. The video shows the virtual discontinuity mapping in one of the scan sections. In general, 4 main discontinuity sets were defined, where set 1 corresponded to a subvertical discontinuity parallel to the deep line of the ore body, sets 2 and 3 corresponded to oblique fractures, and set 4 corresponded to the bedding plane. The orientation, size, and frequency properties are presented in the following table. These values were used to generate discrete fracture networks in the following analysis. This graph and table summarize the rock mass properties for each rock unit considering the generalized Hooke-Brown failure criteria, an industry-accepted standard for rock mass strength estimation. These values were used as inputs for numerical modeling and further analysis in this work. Finally, with regards to pillar stresses, there were no direct stress measurements in the case study mine. Therefore, secondary information from the world stress map was used to estimate the orientation of principal stresses with respect to the mine's excavations. This information was used to account for different stress scenarios in the stress estimation section of this work. In this section, I will introduce some pillar strength estimates using empirical pillar strength equations, and these values will be compared with results obtained from the stochastic discrete element modeling approach for pillar strength estimation. The Hedley-Grant, Trallan and Soder, Lunder and Pakalnis, and NIOSH empirical pillar strength estimation equations were used to estimate the strength of the case study mine pillars considering their width to height ratio and the intact rock strength properties. With these estimations for a 0.8 width to height ratio pillar, we were able to obtain strength estimations between 20 to 60 megapascals. The NIOSH pillar strength empirical equation will be the one in which this work will be focusing the most, not only because it was developed in the same geographic area where the case study mine is located, but also because it is the only formula that accounts for large discontinuity factor. This factor enables to consider the effect of discontinuities in the strength of pillars. The following graph shows a range of pillar strength values for the case study mine, considering each discontinuity set properties. This formula only allows to account for one discontinuity set at a time. Since the bedding plane, or the discontinuity set number 4, is the most continuous discontinuity, the strength of the pillar in the case study mine, considering the effect of discontinuity set 4, was selected as the case study mine pillar strength reference value. Taking into account that the only variable parameter in empirical equations is the intact rock compressive strength, given the intact rock strength standard deviation, it is possible to estimate the pillar strength standard deviation for each of the empirical methods. This initial graph indicates the 95% confidence interval for the case study mine using the NIOSH empirical equation. The following histograms compare these variabilities for different empirical strength estimations for a 0.8 width to height ratio pillar. The table also summarizes the values. Results obtained here will be used to compare numerical pillar strength estimation values. The following figure shows the methodology used for the stochastic discrete element modeling approach for pillar strength estimation. A multi-scale DFN approach was used so only those discontinuities that were large enough to cause a structurally controlled failure in the pillar were accounted for explicitly. This also allowed us to reduce significantly the number of elements in the simulation and therefore the processing time. Three different modeling approaches using the discrete element model were evaluated. The one considering elastic intact blocks with intercepted by discontinuities, a second one using deformable elastic perfectly plastic intact blocks intercepted by discontinuities, and a third one simulating the intact rock using a bonded block method approach also intercepted by discontinuities. The bonded block method was selected since results from this approach yielded reasonable pillar strength values which while still capturing the structurally controlled failure mechanisms within reasonable modeling times. Two approaches were evaluated for pillar strength numerical modeling calibration. One using a synthetic rock mass multi-scale DFN approach, another one using the NIOSH empirical pillar strength industry standard. The NIOSH empirical equation approach was selected over the synthetic rock mass approach. A bonded block non-fractured pillar was calibrated until its compressive strength matched results from the NIOSH empirical equation, assuming no discontinuities. Finally, once the bonded block contact properties were calibrated to the intact pillar strength, the filtered discrete fracture network was used to cut the intact pillar to make a fractured pillar model. A total of 15 stochastic realizations were run to estimate the effect of discontinuities variability on pillar strength. The following graph shows the stochastic results for the discrete element modeling of fractured pillars for three different width to height ratios. The stochastic model enabled to characterize the variability on pillar strength due to the presence of discontinuities. Pillar strength for each width to height scenario showed good fit with the normal distribution. The table below shows the results for the mean and standard deviation for pillar strength at each width to height ratio. This table also compares the mean fractured pillar strength values, the NIOSH intact pillar strength estimation, and the NIOSH case study mean strength estimation. For all three width to height ratios, a coefficient of variation close to 1% was obtained. This value is much lower than the coefficient of variation of the intact rock strength, which is around 13%. This indicates that the variability due to the presence of discontinuities is negligible in comparison with the variability attributed to the intact rock strength variability. In this part, I will talk about stress estimation in the case study mine. Analytical solutions and 2D finite element models are commonly used to estimate stress applied to pillars in underground mine excavations. In this work, the incline pillar stress formula proposed by Parizeau was used to analytically estimate stresses on the pillars in the case study mine. This approach is an extension of the tributary area theory that allows to account for the depth of the deposits. A two-dimensional finite element numerical model was done using the software RS2 from Rock Science. This simulation considered elastic materials and used the generalized Hooke-Brown constitutive model properties that were presented in earlier sections. A cross-section through the center of the study was defined and the gravity-induced field stress was considered, and stresses were measured across the center of the pillars. A finite volume model of the case study mine was performed using the software 3DEC. A simplified 3D mind model was made in Rhinoceros, and the geometry was imported into 3DEC using the plugin Brittle. The pillar stress estimation was performed using an elastic approach and the rock mass elastic properties for each main lithology in the case study mine. 3 stress scenarios were evaluated assuming different vertical to horizontal stress ratios, as shown in the table. From the world stress map, we knew that the maximum principal stress was the one parallel to the strike of the ore body. A fish function was developed to map and calculate average vertical stress for each pillar in the simplified pillar arrangement model. This function assigned a number to each of the pillars, beginning on the bottom left corner pillar with 1 and increasing to the right and then up to pillar number 72 on the top right corner of the pillar arrangement. The function looped through all the zones of each pillar and calculated the average vertical pillar stress by adding all zones' vertical stresses and dividing this by the total number of zones contained in each pillar. Once the average pillar stress was determined, each pillar was colored by this value as indicated in the last figure. This graph summarizes and compares results from the 3D finite volume numerical model, the 2D finite element model, and the analytical solution. As you can see in this graph, all 3 solutions yield different results. Acknowledging that the 3D numerical model allows to account for most of the assumptions that the analytical and 2D numerical solutions consider, we can say that the analytical solution overestimates the stresses, whereas the 2D numerical estimation underestimates these results. Some of the assumptions that explain why the analytical solution yields higher stresses values are that it assumes a flat surface on top of the pillar, it neglects the ground's self-supporting capacity, and ignores the effect of the out-of-the-plane stresses. On the other hand, some of the reasons that explain the stress underestimation of the 2D numerical solution are related to that this assumes that pillars are infinite in length and that the topography maintains constant in the out-of-the-plane direction. From a safe design standpoint, it is recommended not to use a 2D solution to analyze this type of problem, since it was shown in the results that 2D solutions may underestimate stress magnitudes on pillars. In addition, the point estimate method approach was used as a simplified stochastic method to capture potential variability in pillar stress in the case study mine. For this, only the rock mass elastic module was assumed as the variable parameter. This approach allows to estimate the mean and standard deviation from a parameter distribution by only accounting for a limited number of realizations. The tested realizations are selected based on point estimates of the input parameters, and the point estimates are defined based on the mean and standard deviations of each input parameter. There are 2 point estimates for each input parameter. The first one is 1 standard deviation above the mean, and the second one is 1 standard. The following figure summarizes the results of the stochastic stress analysis for each of the considered stress scenarios. Average and standard deviation values are in the same scale for each stress scenario condition. The most unfavorable condition was the one with the horizontal to vertical stress ratio of 1.5, where the highest pillar stress value was of 25 megapascals. For the 1.0 horizontal to vertical stress ratio, the maximum vertical pillar stress was in the order of 20 megapascals, whereas for the 0.5 horizontal to vertical stress ratio, or the least unfavorable condition, a pillar stress value of 17 megapascal was observed. In all 3 scenarios, the pillars with the highest stress values were also those that presented the highest standard deviations. The following graph summarizes the previously shown results. It shows average vertical pillar stress for each of the pillars at different pillar stress scenarios. In addition, the 95% confidence interval was defined using the standard deviation obtained by the point estimate method. In order to understand the obtained results, a plane view of the average pillar stresses was overlaid with the surface contours. It was observed that pillar stress concentration strongly depended on the changes of surface topography. Pillars underneath gullies presented less load than those below the spurs. In addition, pillars located on the abutments carried less load than their fully excavated neighboring pillars. This could be attributed to the self-supporting capacity of the ground or the pressure arc. In this final section, results from both stress and strength estimations are combined to estimate a pillar probability of failure in the case study mine. Finally, results from the numerical modeling approach will be compared with photorealistic 3D models as a way of model validation. Reliability analysis allows to estimate the probability of failure of an engineering system by considering the probability distribution function of the controlling variables. In our case, the only variables that control the stability of the systems are pillar strength and pillar stress. Pillar stress average and standard deviation values were obtained for each of the pillars in the case study mine. In addition, since all pillars in the simplified arrangement have the same geometry, all of them are assumed to have the same strength distribution. The average strength was defined as the strength obtained from the stochastic discrete element model, and the standard deviation was considered as the standard deviation obtained from considering intact rock's compressive strength in the NIOSH empirical equation, since as discussed in the previous chapter, the effect of intact rock variability had a more significant effect in strength variability. A limit state function is defined as the difference between the strength and stress. Therefore, the probability of pillar failure is defined as the probability that the limit state function yield negative values considering the bivariate distribution, assuming that both variables are uncorrelated. The calculation of probability of failure is performed using the following equations that consider the mean and standard deviation for the strength and the stresses. This enabled us to estimate a probability of failure for each pillar in the case study mine. Results are reported into TRIDEC by coloring each pillar with these results. Pillar probabilities of failure were calculated for all three stress scenarios. The following figure shows a plane view of the pillar arrangement colored by the probability of failure overlaid by the surface topography contours. For stress scenario 2, a maximum probability of failure of 0.014% was calculated. For stress scenario 1, a maximum probability of failure of 0.056% was obtained, and for stress scenario 3, a maximum probability of failure of 0.825% was obtained. In all three scenarios, pillars from levels 1 to 4 did not show any significant probability of failure. In the three scenarios, pillars with the highest probabilities of failures were always the same. This figure summarizes pillar probability of failure results. It is possible to observe that pillars 16 and 29 are the ones that present the highest probability of failure in all three scenarios. In addition to probability of failure, factor of safety was also calculated for all the pillars. It is possible to observe that those pillars with a significant probability of failure were also the same ones that presented a factor of safety below the recommended design standard of 1.8 for stone mines in the United States. It is worth mentioning that the actual horizontal to vertical stress conditions of the mine is not determined. These results don't indicate that pillars are not under compliance. This analysis indicates that horizontal to vertical stress ratio is a parameter that has a relevant influence on pillar probability of failure and factor of safety calculation. Therefore, mining operators should invest resources in characterizing this important parameter. The question that arises with these calculations is, what is an acceptable value for a probability of failure? Current pillar design standards are only based on factors of safety. Therefore, there are not any recommendations of what an acceptable probability of failure could be. Probabilities of failure are usually not considered since their interpretation may be more difficult and the word failure is implicit in them. However, designing only based on factors of safety does not make the uncertainty associated to the design parameters to go away. Conversely, this prevents engineers and decision makers to acknowledge the variability associated with these design parameters. Current international ground control best practices recommend the integration of risk management principles to ground control in underground operations. The proposed design approach, based on the estimation of pillar probabilities of failure, offers an additional tool for integrating risk assessment practices into the design of pillars in underground mines. These practices can be adopted in operations through the design and implementation of ground control management plans. One way of defining acceptable probability of failure values is by comparing results from factors of safety and probability of failure obtained from the numerical models and calculations. When comparing these results for the particular case study mine, we can observe that a probability of failure of 0.05% corresponds to the minimum factor of safety recommended in the current stone mine design guidelines of 1.8. This comparison could be implemented in other sites in order to define a particular probability of failure for each specific site. As a way of validation, both pillar stress and pillar strength models were considered together to evaluate the stability of a specific pillar in the underground mine. This particular pillar was also laser scanned and photographed, and results from the simulations were compared with 3D photorealistic models of this pillar underground. The following table summarizes the properties used for the bonded block fractured pillar in this simulation. This model was considered the stresses that specific pillar was subjected in the actual mine. Results from this comparison enabled us to observe maximum displacements in the order of 3 mm. We also observed that areas with larger deformations were located on the faces exposed to the stopes or the drifts. Also, the faces, looking at the crosscuts, had less displacements, particularly areas in the corners where the intersection of discontinuities would occur would present the highest deformations in the model. With regards to pillar stresses, the areas of the pillars that presented less displacement were those that presented higher compressive stresses. The maximum stresses recorded in the simulation were in the order of 21 megapascals. For this particular case, no bonded block failure was observed in this model, indicating that the pillar that was selected for this study did not present any significant failure according to the model. By comparing these results with the resulting point clouds from the laser scans and photogrammetric model, we were able to observe some correlations between both models. In our numerical model, we observed that the areas with larger deformations were in the corners of the pillars where discontinuities would intersect. In our 3D simulations, those areas that we identified with larger deformations were areas where material had been removed from the pillar due to sloughing or scaling in these areas. These pictures shows how the discrete fracture networks used in the simulations resemble the structurally controlled instabilities observed in the periphery of the pillars. As a conclusion, we have that pillar collapses are high-risk events that continue to occur in the United States and abroad. Therefore, risk-based approaches are necessary to design new mines and evaluating legacy workings. In this work, we have proposed a risk-based pillar design methodology that integrates multiple technologies such as laser scanning, discrete fracture network generation, stochastic discrete element modeling, and stochastic finite volume modeling. This methodology was tested in a case study mine. The case study mine presented a main failure mechanism that was defined as structurally controlled. An stochastic discrete element modeling approach integrating the bonded block method as well as the filtered discrete fracture network was used to estimate pillar strength and evaluate the variability of pillar strength due to the presence of discontinuities. We also observed that the stochastic discrete element modeling approach with that bonded block method enables us to represent and reproduce the structurally controlled failure mechanisms while still obtaining variables that were comparable to current industry design standards. For example, the NIOSH empirical strength equation. We also performed a stochastic finite volume modeling approach for estimating the effect of intact rock elastic properties variability on pillar stress in the case study mine. Were combined using the reliability method to estimate pillar probability of failure in the case study mine. This design methodology can be used as a probabilistic risk analysis approach to evaluate and identify areas of the mine that may be of concern. Finally, a stability assessment was performed by comparing results of a particular pillar in the case study mine with results from laser scans and photos that were taken in the mine. These are some of the references for the work, and thank you so much for all your attention.
Okay. Even if he's not here, I would like to thank Mr. Monsalve for his very interesting presentation. And too bad we can't ask him a question directly. But if you are interested in his research, you can contact him at this email address. And now we are at the end of this fifth ISRM Young Members Seminar. On behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would also like to thank Dr. Massud Raju and Mr. Juan Jose Manal for their very interesting and valuable presentation that addressed two relevant topics in rock mechanics and rock engineering. We hope that this seminar provides you new insight and new challenges for future research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. And for this reason, we want to invite you for the next seminar that will be virtually held in June. Dr. Yashwant Kumar Kujala and Mr. U.S. May will present their works respectively on extended finite element procedure for the analysis of reinforced dual permeable rock media and a probabilistic-based approach to rock slope stability analysis in open pit mine using numerical modeling. Further information will be available on ISRM newsletter and website. So keep in touch and not to lose the next webinar. And if you are interested in participating, please contact us by email at the isrm.ym.seminar@gmail.com. Thank you for your participation and have a wonderful and safe day or night, depending by your time.